Good morning, students. Today we will discuss about the Z transformation. Okay. So far, what first we will before starting the session, why the transformation is required? What do you mean by transformation? Why the transformation is required? What is the transformation? Because it is normally it is used for reducing the complexity mathematical operations, reducing the complex mathematical operations into simple ones. So normally it involves some changes in the coordinates and domain of operation. For example, if you want to multiply two large decimal numbers, how do you multiply two large decimal numbers A and B? If you want to multiply two large decimal numbers, normally we preferred in 10th standard I have studied, normally we prefer the logarithmic function. So instead of multiplying these two large decimal numbers, we can go for the logarithmic transformation. So you can do log A plus log B. This is a simple transformation. This is a, instead of multiplying these two, both are two large decimal numbers. Okay, large decimal numbers. If we want to multiply, we can go for the logarithmic transformation. So instead of multiplying, you can transform into log A plus log B. Similarly, in signals and processing also, the transformations are used in signal processing systems mostly for converting the signal in time domain, signal to signals in frequency domain, Okay. So in the last unit we have studied the mathematical foundations, Laplace transformation, and the differential equation, Laplace transformation, Fourier transformation. Okay. Then in that Fourier transformation, discrete time Fourier transformation, discrete Fourier transformation, then fast Fourier transformation in the different algorithms. Similarly, DT systems, the difference equations, mathematical foundations, the difference equations, and the Z transform. Now we are going to discuss about the Z transformation. So in the differential equations and all, it is the differential equation, the difference equations, because the differential equations for analyzing the CT systems, CT systems. So the differential equation is very difficult because which is very complex and is very difficult to analyze the signals in time domain. So that we are transforming this into frequency domain, that is a Laplace transform, that is a S domain. Okay, to analyze the Laplace transform is used to analyze the CT systems in frequency domain and S domain. Similarly, the difference equations also is very complex to analyze the signals in time domain, for DT systems. So for DT system to analyze the signals in frequency domain, we are using Z transform. So before starting the Z transformation, so the classification of systems may be continuous time system and discrete time system. continuous time to discrete time by sampling we are doing, by sampling. So what is what every concept you should know. So CT systems, DT systems. What are the math? So you have attempted all the basic mathematical foundations required to analyze the signals and systems in the last semester. So the Laplace transformation, differential equation, Laplace transformation, and the differential equation Z transformation. To analyze the CT systems in time domain, we are using differential. It is very complex to analyze, so that we are using Laplace transformation, that is a S domain. We are analyzing the signal in frequency domain. In DT, to analyze the systems for DT systems, so instead of analyzing by using difference equation, which is very complex to analyze, so that we are transforming into Z transformation. So why we go for transformation, Z transformation, so it is used, so the Z transformation which is used to take discrete time domain signals. Okay, the Z transform is used to take discrete time domain signals into a discrete time domain signals into a complex variable frequency domain. Complex variable frequency domain. So how you can represent the signal? So Z equal to x of z, which is equal to the summation of n is equal to minus infinity to plus infinity x of n into z power minus n. So remember that this is a Z transformation equation. So the Z is a complex variable. That is a complex variable. So you can represent the Z is equal to, that is R into e power j omega. Okay. So what is R? That is a magnitude of Z. What is omega? The omega is equal to angle of Z. Okay. So this is your Z plane. So you can represent the Z transform as a unit circle. Okay, this is a unit circle. Okay, so the angle Z equal to, so this magnitude is 1. Phase that you can take, this angle is omega. So this angle is omega. So this is, it is Z equal to e power j omega. You take the magnitude will be 1 and the angle is omega. Okay. So now we can define what is the, in that, what do you mean by region of convergence, ROC. How we are studying the S-plane, what is ROC, how the poles are located in the S-plane. So how do you define the region of convergence? This is a region of convergence. Region of convergence. region of convergence. How do you define what are the values of z? How do you define the values of all the values of z, all the values of z for which the x of z, for which the x of z should converge, that means it is finite, or converge, it should be converges. Okay. X of z is finite or converge. So, if for example, if you take that sequence x of n is equal to 1, 2, 3, 4, 5, 6, 7 for the given sequence, the x of z you can write. So, the summation of n equal to 0 to 6, x1 of, that is okay, x1 of n, x of n into z power minus n. So, you can write, so you substitute, so 0, so it will be 1, x of 0 is 1, if it is not specified the starting position is 1, 0th position is 1, plus you will get 2 power 1, so 2 z minus 1 plus 3 z minus 3 plus 4 z minus 4 plus 5 z minus 5 plus 6 z minus 6 plus 7 z minus 7. Okay. So, in this equation if you substitute z equal to 0, if you substitute z equal to 0, so the x of z will be 1 by z, so, okay, anything to be 0 infinity. So, x of z become infinity. Similarly, if you substitute a z equal to, okay, so what is the ROC now you can define for this one, for this x of z. So, ROC will be the entire ROC, okay, entire ROC except at z equal to 0. If this, for example, if the sequence length is, if it is a double, this is a left side sequence 1, 2, 3, you can write, how do you write x of z? So, this is 3, okay, 3 plus, okay, if it is there starting from 3 plus 2 z plus z square. How you substitute here, x of z is equal to the summation of n equal to formula is minus infinity plus infinity x of n into z power minus n. So, this is starting, this is minus 0, minus 1, this is minus 2. So, you can write n equal to minus 2 to 0 into x of n into z minus n. Okay. So, you can expand. So, x of minus 2 into z power minus 2 plus squared plus z x of minus 1 into z power 1 plus 0, x of 0 into z power 0, anything power 0 is 1. So, that I will return straight away, x of 0 is 3, okay, x of 0 is 3, x of minus 1 value is 2 into z, and x of minus 2 is 1 into z square. Okay. So, I straight away you can write, once if this is the formula, this is the x of z, you substitute the limits and expand and substitute the values of the position, the sequence, and write the z transform. So, now in this if you put z equal to infinity, then the ROC, how do you define ROC for this one? So, entire ROC except at z equal to infinity, because if you substitute z equal to infinity, okay, then the x of z becomes infinite. So, what is the condition for ROC? The entire that means all the values of z except, that is for which the x of z is should be finite or converge. So, if you substitute z equal to infinity, it will become infinite. So, that you can write for ROC for this equation the entire ROC except z equal to infinity. So, if you take the 3 examples I will give, if you take x of n is equal to 1, 2, 3, in this case if the position is this is 0th position, then you can write 2, this is 0th position, this is 0th position x of 0, this is x of minus 1, this is x of plus 1. So, you can write 2 plus the right side sequence will be 3 z inverse here z. So, now in this case how do you define ROC? If it is z equal to 0, this x of z will be infinite. Similarly, if z equal to infinite, the x of z will be in this case infinite. So, it will be infinite. So, now what is ROC conclusion is? What is the conclusion of ROC? Entire z plane, all the values of, you can write all the values of z except at z equal to 0 and z equal to infinity. So, you can take so many examples 1, 2, 3, 4, 5, 6, 7. In this case, if the position is now this one, you write the sequence of x of z and what is the ROC you can determine. So, next we will discuss about the properties of Z transform. So, here I am not going to discuss all the properties of Z transform. You can refer the prescribed textbook for all the proofs properties of Z transform. So, in there the properties I list out here, you know what you mean by linearity property, time shifting property, okay. So, so x1 of if x1 of n is equal to x1 of z, then a1 into x1 of n plus a2 into x2 of n, you can write, take z transform a1 into x1 of z plus a2 into x2 of z. Similarly, for time shifting property, you know, for example, x of n is if you take z transform x of z and x of n minus k, the delayed by k samples, the delayed version can be written as z power minus k into x of z. This is the unit delay element. Unit delay element, that is unit delay means z inverse. Okay. If you want to write z minus 2, you should not write z minus 2. Okay, it is wrong. If you want to, the 2 units of delay delayed by 2 sample means z minus 1 and again z minus 1, that is z minus 2. This is the unit delay for the, so this is, it represents only unit delay element. Okay, so this you can write x of n minus k. So how you can write is that x of n minus k can be written as, so this normally we used to frequently used properties already, z power minus k into x of z. Similarly, the other properties are scaling property, okay, scaling property, differentiation property, time reversal property, that is just time reversal property. So, x of minus n means x of z inverse. Then convolution property. So, what do you mean by convolution? You know, convolution property. So, x1 of n convolve x2 of n, take z transform, then it will become x1 of z convolve x2 of z. So, convolution, if the question may be find out the response of the system, LTE system, okay, find out the response of the system. So, y of n, x of n, and this is h of n, output response of the system. You can convolve this x of n in convolve of h of n. If you take this, if it is a dt system, then x1 of z into x2 of z. So for example, find the convolution. Find the convolution if you take x1 of is equal to 1 comma minus 3 comma 2. The position is x2 of n, x2 is equal to 1 comma 2 comma 1. Okay, so how do you write x1 of z here? 1 minus 3 z inverse 3 z inverse plus 2 z minus 2. Similarly, x2 of z is equal to 1 plus 2 z inverse plus z minus 2. So how do you perform the convolution? So x1 of z into x2 of z, which is equal to, that is 1 minus 3 z inverse plus 2 z minus 2 into 1 plus 2 z inverse plus z minus 2. So multiply and simplify the equation. Then you can take inverse z transform to get x of n, again if you want. Okay. So now and one more property we will discuss, the initial value and final value theorem. This question also you can explain. So what is initial value is x of 0, the limits z tends to infinity x of z. Okay. Similarly, x of final value theorem, this is the initial value, final value x of infinity, which is equal to limits z tends to 1 z minus 1 into x of z. Okay. So initial value and final. So I listed only some of the important properties. So to find the initial and final value, we'll take one problem. Find the initial value and find initial and final value. Initial and final value. Find the initial and final value of x of n. If x of z is given by 0.5 z squared by z minus 1 into z squared minus 0.85 z plus 0.35. Okay. So how do you the initial value, how do you find the initial value? So x of 0, x of 0 is equal to the limits z tends to infinity x of z. So in that case, so we will get x of 0, you will get, if you substitute z tends to infinity, it is 0. So we will get 0, this value will be 0. If you want to find final value for this in x of infinity, so in that case limit z tends to 1, so z minus 1 into x of z. So in that case the z minus 1 will be cancelled, so the remaining part will be 0.5. Okay, here it will be cancelled. So z equal to 1 is substitute, so 1 minus 0.85 minus plus 0.35. Okay, so approximately equal to 1. So x of infinity is equal to 1. So x of 0 is equal to 0 and x of infinity is equal to 1. This is the initial value and final. Next topic we will go for the pole. So how do you determine, how do you define a pole? Okay, this is how do you define a pole? What do you mean by pole? So already we discussed about the pole. The pole plays a vital role to determine the stability of the system. So in a Laplace transformation, how the poles are located, we have analyzed. So, here in this Z transformation also how to define a pole we will discuss. Okay. So, how do you define a pole? So, the pole, the system has a pole, the system has a pole at which the system has a pole at which the amplitude of the system becomes infinite, at which the amplitude, the system has a pole at which the amplitude of the system becomes infinite, okay. So, now what is meant by pole? So, the pole is nothing but the pole of a given function in that point at which the amplitude of the function becomes infinite. Normally, the system output to be a finite amplitude. The system output should be a, what is the requirement? The system output should be a finite amplitude. System should be finite amplitude. Okay, finite amplitude. System function should be a finite amplitude. So, we must avoid operating the system in the region of poles of the transfer function. Okay. So, we should avoid, we must avoiding the system in the region of the poles of transfer function. So, you know what is a transfer function? Normally the h of s. So, this is a CLTI system, DT systems. The input is x of n. This is the system function. So, normally x convolution you can define y of n. So, this is a system impulse response okay, h of n. You can determine the output for any input if you know the impulse response of the system x of n convol h of n. Okay, now, if you take Z transformation, so the system function is denoted by h system function. Okay, so you take x of, so you take Z transform. So, y of z is equal to x of z into h of z. So, y of z by x of z is equal to h of z. So, the y of is a rational function. So, the y of z by x of z is the numerator polynomial of the system. So, the y of z, so this is a numerator polynomial coefficients, numerator polynomial coefficient divided by denominator polynomial coefficients. Okay. So, if the denominator, so the numerator polynomial of the system is called normally. So, normally the system function, so the numerator polynomial by denominator polynomial coefficients. So, the numerator polynomial coefficients of the system is called zeros of the system. The denominator polynomial coefficients are called poles of the system. Okay, zeros of the system, poles of the system. So, if the denominator polynomial coefficient, if the residues, so that is normally you can write zeros, no. So, z minus z1, okay, z minus z2, like that it will go. Denominator polynomial coefficients are poles of the system, z minus p1, z minus p2, like that. If any one of the residues are equal to 0, okay, if any one of the residues z1 equal to, that is the zeros of the system, z1 equal to z. So the numerator polynomial becomes 0. So 0 divided by anything divided by 0 divided by anything 0. So zeros are the system. If any one of the poles, if z equal to p1, okay, this residues, if any one of the residues is equal to z, then the denominator polynomial coefficients, okay, this will be, the denominator function will be 0. So anything to be 0, infinite. Okay, so 1 by 0, infinite. So the, as I said, if it is, if our system should not operate in the infinite amplitude, infinite mode. Okay, our system, we should not operate in the infinite mode. So we must avoid operating the system in the region of poles of the transfer function. Okay. So now for a given function, you should be able to find out the poles of the system. Okay. And what is the question may be, what is ROC? How do you determine the poles, okay, for the given transfer function? So the basic for the transformation, we'll take one example, x of n. How do you define? I'll tell you, a power n into u of n. So what is u of n? Whenever u of n is equal to the mathematical deterministic signal, u of n equal to 1 for n is greater than or equal to 0, which is equal to 0 otherwise. So how do you mathematical representation? This is u of n, so which is equal to 1. This is 1. So this is 1. So u of n is equal to 1 for n is greater than or equal to 0. So this is a mathematical representation. So now if you find x of z, determine the x of z. So the summation of n equal to minus infinity to plus infinity, a power x of n into, this is the x of n, you write the formula, x of n into z power minus n. So now what is x of n? N equal to minus infinity to plus infinity, x of n is a power n into u of n, z power minus n. Okay, this one you can write the summation of n equal to, this will be 0 to n will be, this is 0 to infinity, this is infinity, okay, 0 to infinity, this will become 1. So you can write 1, so you can simplify the a term and z term, a, okay, a z minus 1 z inverse e power of n, u of n will become 1 from 0 to infinity. Okay, now so what is the summation of n equal to 0 to infinity a power n, which is equal to 1 by 1 minus a. This is a 1 plus a square plus up to infinity. If a is less than 1, then you can use this formula. Okay. So now you can write x of z is equal to, so 1 divided by 1 minus a. What is a? This is a. This is a power n. So 1 divided by 1 minus a is z inverse. Okay, a is z inverse. So this you can write 1 divided by 1 minus a by z. So you can write 1 divided by z minus a by z. Finally you can write z by z minus a. So now what is a pole? Now what is a pole? The denominator only denotes the pole, no? Z equal to a. What is a 0? Z equal to 0. So the x of z is a rational number, is a rational function. X of z is a rational function, is a rational function. Rational function which is characterized by, okay, 0 and poles. The roots of the, so the x of z is a rational, so x of z is a rational function which is characterized by its 0 and its poles. So what is zeros? Numerator polynomial coefficient, the roots of the numerator polynomial and the poles are the roots of the denominator polynomial. So now 1 0 in this transfer for this function, rational function, as 1 0 at z equal to 0 and 1 pole at z equal to a. Okay, now how do you determine the ROC? So region of convergence. The system should have, what is the system should have finite amplitude. For the system should have finite amplitude, So completely we solve one problem like this. You can practice other for a given function. So 1 minus the denominator is 1 minus a z inverse should be greater than 0. If it is 0 means 1 by 0 infinity, we should not operate the system in the infinite mode. So it must be greater than 0. So 1 is greater than a z inverse. Okay. So 1 is greater than a by z. Again z is greater than a. Okay. So now how you can write the x of z is equal to 1 by 1 minus a z inverse has finite values of amplitude in the area, where the modulus of z is modulus of z is greater than a. Okay. So what is z actually? So the magnitude of z is equal to this e power j omega. Okay. So you can write cos omega plus j sin omega. So what is magnitude of z? Cos square theta plus sin square theta will be 1. It represents unit circle. Okay, so unit circle. So modulus of z should be greater than or equal to a. So now for unit C here, for unit circle, for this unit circle, this is a z plane. Okay. This is a unit circle, this is r is equal to 1. So this place equal to 1. This is the only ROC, and in ROC is stable and causal unit circle. Okay. So now for this you can draw so in the z plane r is equal to a. R is equal to a. This is your non-causal region. Okay. So this is your ROC. This is your ROC. So modulus of z should be greater than a. What is ROC here? Modulus of z should be greater than a. So modulus of z is greater than a. This is the ROC. So this is ROC. This is the causal region, ROC and causal region. causal region. Okay. So, with this we will complete this session. So, next session we will discuss more problems and find out the ROC and the poles of the transformation. Then we will discuss the properties of ROC. You can refer how the system will be stable. This week in class, next class we will discuss about the whether the, because the poles only determine the stability of the system. So, we can classify into the system may be stable and causal system, or it may be unstable, okay, unstable and causal system, or it may be stable and non-causal system, and unstable and non-causal system, unstable and non-causal. We can classify the system into different categories: stable and causal, unstable and causal, stable, depending upon the poles. You have to determine the poles of the system. So, whether this is for the given function, whether the system is stable or not, how the poles should be located. Okay. So, the properties, if you see here the properties, I can list out the important properties out of so many properties. Okay. The ROC that is ROC of x of z, ROC of x of z, you can convert of a ring in the z plane, no. Say then ROC condition, the ROC does not contain any poles, does not contain any poles. So, normally the z plane at the origin is a ring, z plane is a ring. Okay. So, ROC x of z consists of a ring in the z plane, the origin. So, the ROC does not contain any poles. So, normally we know that if x of s is finite duration, then the ROC is entire z plane at x equal to, except z equal to 0 and or z equal to infinity. So, if x of n is a finite duration, then the ROC will be is the entire z plane except the possible, except the condition, possible conditions z equal to 0 and or z equal to infinity. Okay. And the next session we will discuss about the how the what are the conditions for the stable system. So, here I will conclude with this table also. The stable system, the system becomes stable, system becomes, the system becomes stable if and only if, the ROC of the system function, ROC of the system function, ROC of the system function contains the unit circle, contains the unit circle. ROC contains unit circle, ROC contains unit circle. If the ROC contains unit circle, then the system is stable system. When the system is stable if the ROC contains the unit circle. Okay. And this system has not only single pole, the system may be have multiple poles. So when it has multiple poles, how do you determine the stability of the system? So that and all will discuss in detail in the next session. Okay. So with this I can conclude the introduction about the Z transformation. Thank you.